Hey guys, and welcome back to another video on the channel. In today's video we're going to be solving an application of a differential equation. This is a specific question we will be taking a look at. We actually have covered this before a long time ago, but the video isn't as great because the computer was overheating, so I'm just going to be redoing the problem again today. But yeah, let's get straight into it. So this is from the specialist textbook for QCAA. So example 21, an inverted cone with a height of h centimeters and a radius length of r centimeters. It is being filled with water, which is flowing from a tap at k liters per minute. The depth of the water in the cone is x centimeters at time t minutes. Construct an appropriate differential equation for dx dt and solve it, given that initially the cone is empty. Okay, so straight off the back, we're looking at this scenario and we're imagining there's like some tap here and water's going into it, and we can see it slowly filling up. So that means x is a function of time pretty much. So we're just imagining we're going to get some equation x and we're going to have some t's involved pretty much that tell me how pretty much full this gets. So for example, if I put in t equals 10, it will tell me the height is here, or when like t equals 5, the height's like here, etc. Now, we're also given an initial condition. So the initial condition will be able to find our plus c when we integrate it later. So initially the cone is empty. So what that means is initially, that means when t equals 0, okay? So the start. And when the cone is empty, x must be 0, because it would be down here. So that means x equals 0. So that's some initial conditions we need to keep in mind for later. So when t equals 0, x is 0. Righto, so dx dt is what we're trying to find. But let's see what else have we been given. We've been given that it's being filled with water from a tap at k liters per minute. So liters per minute is a change in volume with a change in time. Now they've said it in liters. Now 1 liter is 1,000 cubic centimeters. Now the reason why I'm doing this is because the rest of the question is in centimeters. So rather than saying k liters per minute, I'm going to say it's 1,000 k centimeters cubed instead. Okay? Now, if I want to find dx dt, we could use an application of the chain rule. So, we have t on the bottom of our denominator, so dx dt is going to be equal to this multiplied by something. Now, in order to get dx on the top, we need a dx here. And we want to get rid of this dv, so we need a dv here. So, in other words, if we want to find dx dt, we've been given this in the question, but we need to find this straight away. Because if I were to multiply these, the dv's can cancel out and you'll get dx dt pretty much. Okay? So, finding dx dv. Well, we see it is a cone. Now the volume of a cone is given by this formula here for just any general shape. So it's 1/3 pi, the radius squared times the height. So if I were to input whatever the height is and the radius, I could, so that's the diameter, so half of that would give me the volume of it. Now, the volume itself is a function of time. Because you see, we have two cones. We have the maximum cone and we have the cone that's changing as it's filling. As you put in more water, the cone is going to be pretty much changing, the blue one. So, we need to express that as a function. So, what we're going to do is pretty much name this guy here. We'll call it y. So y is a variable for your radius pretty much. Because if you pour more water in, your radius is constantly changing. It's constantly getting bigger or smaller if it was getting drained as well. So we're going to name that y. So y is the radius at a point in time. So y is the radius at a point in time. So for example, when the cone is fully full, r will equal y, so when it's up there. Now x, we can see, is the height at a point in time. So, if I want the volume at a point in time, I can just replace my r with my y, and my x with my, my h with my x, sorry. So that means the volume at a point in time is going to be 1/3 pi y squared times by x. Okay. Now, we have a bit of a problem here. We have a function with two variables in it. So we need to try and break this down. Now, this is where a bit of a trick comes in. Because it's a cone, if we were to cut this in half, we could break it into actually similar triangles. So what I mean by this is, if I move this stuff to the side, I'll move that all down there, I reckon. So if I were to cut this down into a triangle, we could cut it like this. So for example, that's X, that's Y, this bit here is H, and this bit here is R. The ratios, we can see they're both similar triangles, so that means the ratio between these two variables is the same as the ratio between these two variables. So in other words, Y divided by R is the same as X divided by H. Now, R and H are constants. They are the volume of this particular cone. Okay? So if I move the R over here, I have Y in terms of X. So if I were to substitute this expression down here, I will only have a function of one variable, just X. So in other words, I'm just going to put this guy down there. So if I do that, I'm going to have V equals 1/3 pi, and this whole thing squared. So X R on H squared times by X. Okay? So if we were to expand this using our index laws, we can apply the square to each of the specific terms. So we'd have X squared, R squared on H squared times by X. We can see those are the same variable, so we add one to the indice. So we have X cubed, and I'll just rub out that X now. And that is our expression for our volume. Now, we were looking for dx dv. If I were to differentiate this, I can get dv dx, which is a step closer. Now, if I look at this closely, if I just get a different color, all of that is a constant. So all we're differentiating is the cube term. So if I were to differentiate that, I'd have dv dx. I bring that 3 down the front, so that cancels out the third. So I get pi r squared h squared x squared, and that's it. Now if I want dx dv, I just flip the entire equation. So what that means is I'll just go, alright, dx dv, I flip everything. So I'm going to have h squared on pi r squared x squared, and that's it. That's my expression for dx dv. So we said before that dx dt is what we're trying to find, okay? And we said that was equal to dx dv times by dv dt. Now we got given dv dt, it's how much it's filling up. It was 1000 k centimeters cubed. So if I take this guy and multiply by this, I'll have dx dt. So dx dt is going to be h squared pi r squared x squared times by 1000 k. Now k is a constant, okay? So dx dt 1000 k h squared on pi r squared x squared, okay? So that is your differential equation. Now it said construct it and then solve it with the initial conditions. Now the initial conditions when t equals 0, x equals 0. So we'll put that down there, so we'll need that soon. So x equals 0 when t equals 0. So we can do this by separation of variables. So I can move the x squared term up there. So I have x squared dx dt gives me this entire thing here. Then I can move that dt up there. So I have x squared dx gives you 1000 k h squared pi r squared dt. And we can see I've separated all my variables, so I can integrate both sides, okay? This side here is very easy to integrate. You add 1 to the power and divide by that new power plus your constant of integration. Here you just attach a variable because there's no other t present. So it's going to be 1000 k h squared pi r squared and shove a t there. And you can put your constant here if you want, but that's just the same as moving it to the other side. So you only need a constant on one side, okay? Righto, so now we're going to use our initial condition. So when x equals 0, t equals 0. So if I put 0 there and 0 there, I'm going to have 0 plus c gives you 0. So that means c must be 0. So in other words, I just write this equation again, but without the c. And that is my function at the moment. Now, we want it as a function of time. So in other words, we want x purely as a subject. So move the 3 up there. So we get x cubed is 3000 kh squared on pi r squared times t. And now we want to cube root both sides to cancel out that cube. And that is your function of time. That gives you the height at any point. So if I plug in t equals something, it will give me the height of wherever the water is, pretty much. And that's how you solve that question there, okay? Hopefully you enjoyed that video. If you did, like and subscribe, and yeah, stay tuned for the next one.